Hello again, everybody. We are now onto something very exciting, which is called something called the multiple linear regression model. And the reason that I get excited by this is because we're now kind of bringing together some of our thinking about understanding where data comes from and understanding how we draw conclusions from data, testing hypotheses and so on. But the ingredient that we need to add to that is some kind of way of thinking about the relationships between variables. And that's where you come up with the idea of a model. A model really defines the relationship between one variable over here and another variable over there, perhaps a characteristic of the company that you're working for, or some of the characteristics of that company, and then the profitability of that company being some kind of outcome variable. And the reason that's so interesting and powerful is because this is where we start to explain what's actually going on in the world. And we use models as our tool for explanation in the first instance. We also use it for predicting as well, which we'll get to in a couple of videos. So we have kind of touched a little bit on what's called the simple linear regression model so far. And the simple linear regression model is essentially a model that relates a variable y to another variable x. And it's called simple because there's only one x variable in there. And effectively this model, if you recall the video that we recorded a few videos ago, is describing the equation for a line which defines the relationship between y and x. So it says on average there is a linear relationship between x and y. So as x goes up, y will change in a linear way, and the extent to which y changes is determined by this slope coefficient here, beta 1. If it's positive, then as x goes up, y goes up. If it's negative, as x goes up, y goes down. And this beta naught here, so that's the slope, the beta 1, and the beta naught represents the intercept, the value of y that your model predicts when x equals 0. So that's our kind of linear equation, which we use as our description of our simplest of models. And so, for example, in the case that we have looked at earlier, we might be interested in y being the education level, income of a person, and on the right hand side we've got some x variable. So in this case we're going to say that the x variable on the right hand side is your level of education. So how many years of education have you had? And one would assume that the more years of education you've had, the higher your wages. So we want to see if that's true, and use this kind of as a little bit of a model to explain why it is that some people earn more than others. And that's, starting to get to some pretty interesting and important social questions or economic questions. So we use Excel or any spreadsheet program to take our column of data on education, call that X, and our column of data on wages, call that Y, and run it through the regression model, and out spits the results that look like this. And so you can see here we've got the most important bit is this little couple of numbers here. Those are the estimated values of the intercept and the slope, minus 44,000 for the intercept and a slope of 5,597. So we need to understand what those numbers mean. We also need to kind of do just a little bit of checking as to whether we've got a sensible model, whether the variables are relevant, all those sorts of things. And so various bits of output of this thing here give you some clues about that. But we're going to, before we kind of go into greater detail about how these models work, we need to just ask ourselves the question whether we've got a decent model or not, whether it's a sensible model. And it's pretty clear to us that we've got a bit of a problem if we think that wages are determined purely by people's education. We're not saying that's exactly the case. We've got what's called an error term in this. So we know that if you know someone's education, you can't exactly predict their wage. But by specifying this simple equation here, we're saying, look, the only sort of measurable quantity that really matters if you want to try and explain someone's wage is their education level. And we know there are other factors that would matter to how much wage a person earns. So for example, suppose we had another variable x2, which might represent the age of a person. So this would say to us that if we just estimate the model we've estimated so far, then we're assuming that your income is determined by your education. So it doesn't matter how old you are, it doesn't matter if you're 30 or 50 or 60, you earn the same, at least the model predicts you on average that you'll earn the same if you're for a given level of education. Now that's unlikely to be true. So we kind of leaving the variable age out and it's going to be a problem for us. Age is kind of often very important to income because age kind of is a bit of a proxy for experience. The longer you're working, you tend to get promoted, recognition of your experience, you go into more senior roles in management and so on, and you earn more money. So age is usually positively correlated with income. Now, the problem is that if in our first model, we showed here that education has a very strong positive effect on income. The more educated you are, the more income you earn. Okay, no problem with that at all. Now, what we're going to sort of reason through here is that some of that, when you ignore something that you know is important, which is age, some of that apparent effect of education could actually be just an effect of age. Because it turns out that people who are more educated are actually, in the sample at least, are typically older. So there's a positive correlation between age and education. That's just the way it works out, so in our particular sample. So we've got, and that's actually partly because we've got people in the age range 20 to 30, so some of the younger ones in the low, aged in the low 20s haven't had time to complete their education yet. So the younger you are, then the lower your education level tends to be for this particular sample of 20 to 30-year-olds. So we end up with a positive correlation here. So when we did the model where we just estimated the relationship between education and income, we were partly capturing some of the effect of age on income. And so part of that, what we thought was education, actually may not be education. It just might be that some of the people are older and earning more income. It happens to be that if they're older, they're also likely to be more educated. That's what this correlation here says. So what we've done by leaving out the variable age is create a bias in our estimation of the effect of education on income, and that's what's called the omitted variable bias. If you leave out a variable that matters, you will end up possibly creating a bias in the variable that you do have in the model. And that bias will be determined by the correlation between the variable you've left out and the variable you included. That's kind of pretty intuitive. Let's actually see it in some numbers. And so if we skip down, for example, let's go, I'm going to come back to the previous slide. Let's go to this result here. When we add age into the model, you'll notice we still have an effect, positive effect of education, 4,395. But notice it's smaller than it was before. Just taking you back, remember that number 4395, go back a couple of screens and you see it was 5,597. So some of that effect of education on income actually is not education driving income, it's actually age driving income. And we've, in the simple regression model here, in the absence of age in the model, it's captured by the education effect. That's the omitted variable bias. So that number there says, if you just treated that number as the truth, if you go out there and spend more time in education, every extra year of education you get will deliver you an extra nearly $5,600 of income. Great news. So you tell people to go out and pursue education. It's worth it if it's going to generate you so much extra income per year. But actually, that would be misleading to people, because some of that effect is not real. Some of that is just the age effect. And in fact, they're only going to get about $4,400 extra per year for every extra year of education they get. Okay, that's quite tricky to get, but the main point I want you to get from it is that it's a reminder to us that any time you specify a regression model and estimate it, you have to think about what other factors might be missing from this model. And that's going to be particularly problematic if you've only got a simple regression model. You've only got one X variable. There's bound to be other factors that you've left out. And as soon as you do that, you may well end up creating an effect that is not a true effect. It's kind of proxying for the variable that you've omitted from the model. Okay, so you kind of, there's no guarantee that just because it looks like a nice model and it's a nice big number and it's very everything looks very good, there's no guarantee you get the right answer, and the model specification really matters to that. Have I included all the variables that really matter here? So you're going to have to include more than just one X to get the real story. So to do that in Excel, it's exactly the same as the simple linear regression case, except instead of choosing one column for X, you choose a set of columns. They have to be right next to each other in Excel. You can't have column A, B, and E. You have to stick the three columns together, ABC or EFG, doesn't matter what they are, and then select those three columns together in your X part or your independent variables in the multiple regression thing. When you do that, you get your output looking a bit like this, and we can interpret those variables as we will in just a moment. Now, what do they actually tell us? Okay, well, the answer is that, let's think about these one at a time. Remember, the regression model is just like fitting a line through some data. So the intercept is the predicted value of y when x equals 0. Okay, it's where we cross the line. But we've now got more than one x here. So the interpretation still holds, but we have to now just create a little bit more of a mouthful for ourselves as to what we're saying here. The intercept tells us what would the predicted income be of a person who has no education and who is aged 0. So it's a little bit of an unusual thing. Not too many people. So as I was saying, a person who's got 0 years of education and who's aged 0 is not a particularly realistic person. But if we did have such a person, then the model predicts that their income would actually be minus 115,000, which of course is even less realistic. People don't tend to earn negative incomes. So this does often happen with your intercept. Often the intercept doesn't make a lot of sense. It's kind of a range of the X data that's not realistic. You don't have anybody in your sample age 0. In fact, the youngest person in our sample is age 20. So the model's not going to do very well at predicting the income of brand new babies. And sure enough, that's what you find here. It predicts a silly level of income of minus 115,000. But strictly speaking, that's what we mean by the intercept, the estimated value y when the x is a 0. The two other coefficients are what's called slopes, but these slopes are a little bit different. They have to take account of the other variables. So, for example, education 4395 says if we add another year to someone's education, then on average that will increase their income by 4,395 if you hold their age constant. So you've got to hold the other variable constant. So don't change the age, just change the education level, and this will tell you how much the income will increase by. Then the 3465 tells you the opposite. Take two people with the same level of education, but one of them is a year older than the other. This second person, the one who's older, will have an extra $3,465 of income per year on average. Okay, so there's the discussion about the intercept, and then the next page we have the interpretation of the two slope coefficients. The effective education is the first one. Take two people of the same age, one of whom has had an extra year of education than the other, but notice of the same age, so hold that other x constant. And this model says that the person with a higher level of education will earn this much more. And then we have a similar interpretation of the coefficient of age. Okay, so that's how you interpret slopes in a multiple regression context. That extra dimension of holding the other x variables constant is quite important. So the beauty of it is, the powerful thing about it is that you've now been able to isolate out the effect of one variable independent of all the other variables, just so that you can say this is a purer, or more pure, not perfect, but a more pure effect, for example, of getting more education on your income. Now, how would I use this model? Well, apart from anything else, the interpretation itself is quite interesting. It tells me, what in the direct sense, for example, what the effect of an extra year of education will be. But I could also use the model to predict the wage of a particular person. So this is my model, the intercept plus the first slope times the level of education plus the second slope times the age. If I have some particular x values, I can plug them in. If I have a person who's got 12 years of education and who's age 30, I can plug those into this equation and calculate out that the model predicts that this person will earn $41,081 per year. So that's using the model for prediction. Common that you might actually want to do that. The next thing you might want to do with your multiple regression model is test a hypothesis about the slope. And the reason this is particularly important is because there's something special about the slope being 0. If the slope is 0, for example, the slope on the education variable was 0, which is beta 1, this tells us that there's no relationship between education and income, if that was the truth. Because is that a slope of 0 means as you increase your education, your income doesn't change. So there's no relationship between the two of them. So that's a fairly important kind of hypothesis to be testing. If the slope is 0, you're saying there's no relationship between these two variables. And, sometimes you might find that's the case. You might think there's a variable that's important and relevant, but it turns out not to be. So we need to be able to do tests like that, hypothesis tests like that. All the steps are pretty simple. We just state a null and alternative hypothesis. In this case, we're pretty sure that more education will lead to higher incomes. So we're going to have an alternative hypothesis, which is one-sided, greater than, positive slope. Choose a significance level, look at the p-value, and the p-value is in the output. I'll just show you where that is this column here for education, 2.934 times 10 to the minus 72. It is absolutely tiny. 10 to the minus 72 means 71 zeros, 0.0000 and something at the end. So we're going to take that and divide it by 2 strictly because we're doing a one-sided test, and that's clearly less than 5%, 0.05. So we reject the null hypothesis, and we conclude that indeed there is a positive influence between education and wages. Okay, so we've found out that this variable is important in affecting income. So by scanning down the p-value column, we can see that all the variables are important. Age also has a positive and significant effect because that p-value is very small, and obviously the intercept is significant as well, although that's not that interesting to us. Okay. Now, I'm just going to briefly talk a little bit about the idea of multiple regression from a mathematical point of view. And the key thing I want you to grasp is this idea of an error here. Remember, what we're doing is just think about this as like the scatter diagram that we drew in a few videos earlier. And we've got y and x, and we've got the actual relationship between y and x, the actual dot on the graph, which represents the value of x and the value of y. And then we've got the model's prediction, which is a line that goes through the middle of all those dots. The difference between the prediction and the actual, or the actual and the predicted, to be precise, is the error. And that error will give you some idea about how accurate, the size of that error will give you some idea about how accurate your model is. Now that was true when we had simple regression. It's just as true with multiple regression. What does the model predict the value of y will be? That's this bit. What's the actual value of y? Subtract the prediction from the actual and you get the error. Now, essentially, multiple regression does the same as simple regression. It chooses the values of the intercept and the slopes in order to minimize the sum of the squared errors. So make those errors as small as possible. It sticks the line through the data that makes the errors as small as possible on average by minimizing the sum of squared errors. So how we do that requires us to solve this rather complicated looking mathematical function, and there is some differentiation that we can do and some rearranging and so on, and it turns out that it's quite a complicated set of equations, but effectively with some second-year econometric study, you'll be able to work out how to do that. So for now, you just have to trust us that when Excel spits out the coefficients at the end, that's what it's done. It's found the model which fits the data the best in terms of minimizing the sum of squared errors. Okay, that's enough for now. Thank you.